Hello, my name is Niyati Padman, and I'm a junior at Lake Nona High School, located in Orlando, Florida. Titan, the second largest moon in the solar system, and Saturn's largest moon. If we wanted a spacecraft to land on Titan, what must we consider? In this video, I will be covering three major components for consideration. Number 1, entry, descent, and landing risks. Number 2, extreme temperatures. And number 3, radiation risks. Before we begin, SWAP is an important consideration. This stands for size, weight, and power, and is a critical factor in space missions, especially for distant destinations like Titan. Falcon Heavy is a perfect match for such missions, offering a payload capacity of 63,800 kilograms and a 5.2 meter fairing diameter. With its powerful engines and ample space, Falcon Heavy can carry large spacecrafts and instruments needed for a mission like Titan. Titan's atmosphere is 50% denser than Earth's, and visible light can't penetrate it. This causes major challenges during entry, including managing high aerodynamic forces and heat buildup. I will be addressing how to manage friction and heat during atmospheric entry. We can use a dual-layer heat shield. The first layer is made of phenolic impregnated carbon ablator, also known as pica, which absorbs and dissipates the heat during atmospheric entry. The second layer is reinforced carbon-carbon composites used to withstand the extreme temperatures during descent. Titan's thick atmosphere requires a multi-stage parachute system. First, a drogue chute stabilizes and slows Fermata. Then, a main parachute deploys to slow Fermata even further, taking advantage of Titan's dense atmosphere. Titan's gravity is 14% of Earth's gravity, which provides a greater advantage for slowing down Fermata due to less force on the spacecraft. Once we're closer to the surface, we can use retro rockets to ensure a soft landing. Airbags are deployed to absorb shocks if we land on hard or uneven surfaces, and amphibious flotation devices will keep Fermata afloat if it lands in one of Titan's methane lakes. Titan's surface temperature is incredibly cold, with temperatures around negative 182.55 degrees Celsius. This extreme cold could cause materials to freeze, potentially damaging the spacecraft. To protect Fermata from Titan's cold, we can use advanced aerogel and multi-layer insulation, also known as MLI, and these are similar to what was used on the James Webb Space Telescope. Aerogels will be used for internal insulation to ensure instruments, fuel lines, and other systems maintain operational temperatures in Titan's extreme cold. MLI will be wrapped around Fermata's external structure to minimize radiative heat loss during the journey through space and protect against heating during atmospheric entry. A radioisotope thermoelectric generator, also known as an RTG, serves as both a power source and heating element, providing electricity and warmth for critical systems. We can use cryogenically stable materials like titanium and aluminum lithium alloys, which retain their strength at low temperatures. Flexible polymers are used for seals and tubing to prevent brittlness. Finally, radiation risks. Saturn's powerful magnetosphere emits high-energy radiation, which can damage sensitive spacecraft electronics and instruments. Fermata's electronics can be protected by encasing them in heavy-duty materials like tungsten or tantalum, which block harmful radiation. Multi-layered sheets made from polyethylene add further protection against charged particles. In addition, triple modular redundancy, also known as TMR, is used to safeguard electronics. This means that 3 independent processors perform the same calculation and the majority vote determines the outcome, ensuring that if one gets affected by radiation, the others continue to work. Fermata's orbit can be designed to avoid prolonged exposure to Saturn's radiation zones. By entering Titan's orbit at a specific angle, Fermata minimizes its time spent in high radiation areas. Fermata should be in low energy transfer orbit around Titan before the descent so that the spacecraft can perform system checks and prepare for landing without being in intense radiation zones. To slow down, Fermata uses aerobraking, a maneuver where Fermata flies through Titan's atmosphere to slow down. This saves fuel and reduces speed before final descent. Due to long communication delay of around 90 minutes, Fermata must rely on autonomous systems to manage descent and landing. This allows for real-time adjustments during the landing process. As we have seen, landing on Titan requires a combination of innovative technologies like heat shields, parachutes, radiation protection, and advanced materials to survive the extreme cold and radiation, as well as to ensure a safe landing on Titan's diverse surface. These engineering solutions allow us to explore Titan's mysterious surface and gather data that could provide valuable insights into the origins of life and the potential for further human exploration.